towards artificial general intelligence, insights from a cognitive model. This dissertation explores the potential of a cognitive model inspired by human perception and action to inform the development of artificial general intelligence, AGI. By analyzing the key components of the model, sensation, perception, action, and the interplay between them, we can identify crucial aspects that need to be incorporated into AGI systems. The research investigates how this model can guide the design of AGI architectures, focusing on areas such as representation learning, decision-making, and embodiment. Introduction. Background on AGI. AGI refers to highly autonomous systems capable of performing tasks that typically require human intelligence. These systems not only execute predefined tasks, but also adapt to new challenges in dynamic environments. The major hurdles in achieving AGI include dealing with complexity, learning from limited data, and understanding the interaction of sensory inputs with actions. Motivation for the model. The chosen cognitive model, which focuses on the essential functions of sensation, perception, and action, directly addresses key gaps in existing AI systems. This model's incorporation of self-reflection, integrating a feedback loop for continuous learning, could greatly contribute to building an adaptable, autonomous AGI system. Research questions. How can the model's representation of sensation and perception be used to develop robust and flexible AI systems? How can action and decision-making frameworks be integrated into AGI architectures? How can the model's self-reflection component enable learning, adaptation, and improved decision-making in AGI systems? Chapter 1. Cognitive Model Analysis. Detailed analysis of the model. The cognitive model includes the following components: sensation, the Z1 perception, Z2, and action Z. The dynamic relationship between these components forms a cycle that enables continuous feedback and adaptation. Relation to human cognition. Drawing on theories such as George Kelly's personal construct theory, this model emphasizes the importance of categorization and perception in human cognition. It parallels how humans synthesize new experiences with past knowledge to adapt to their environment. Relevance for AGI. These components reflect the necessary building blocks for creating intelligent systems that can sense, perceive, act, and adjust to changing situations. Core capabilities for AGI. Chapter 2. Representation learning for AGI. Sensation and perception in the model. These are the foundational stages of building representations of the environment. Understanding the role of Z1 and Z2 in processing sensory information and forming useful abstractions is key for designing AGI systems that can generalize from diverse inputs. Representation learning techniques. Representation learning methods, such as deep learning and symbolic AI, can be adapted to model the nuanced sensory input and abstract reasoning seen in humans. Deep networks, for instance, could be used to extract meaningful features from raw sensory data, while symbolic methods may represent higher-level abstractions. Embodiment and grounding. Embodiment refers to the importance of the physical presence of the system in the world, allowing it to interact and perceive the environment. The model suggests that grounding representations in actual physical interaction enables AGI to form more accurate and adaptive models of reality. Chapter 3. Decision-making and action in AGI action and motoric systems. This chapter investigates how motor systems, which translate decision-making into physical output, can be modeled to ensure that AGI systems can interact with the world in meaningful ways. Decision-making frameworks. Various decision-making paradigms like reinforcement learning, RL, and planning algorithms can be explored to define how AGI can select actions. These models allow the system to set goals and identify the best course of action to achieve them, considering the constraints of the environment. Goal-directed behavior. The model's focus on self-reflection and action points to goal-oriented behavior as a driving force in AGI. Self-reflection allows the system to set goals, analyze its progress, and adapt accordingly, mirroring the human capacity for intentionality. Chapter 4. Self-reflection and learning in AGI. Self-reflection in the model. The Z component represents self-awareness, which enables the system to critique its own performance, evaluate outcomes, and integrate learning into future behavior. Meta-learning and continual learning. Meta-learning, or learning how to learn, allows AGI systems to adapt to new tasks without forgetting previously acquired knowledge. Continual learning facilitates lifelong adaptation in dynamic environments, addressing the challenge of catastrophic forgetting. Explainability and interpretability. Self-reflection enhances explainability, as systems can assess and explain their decisions. This is essential for trust in AGI systems, especially in critical decision-making applications. Chapter 5. AGI Architecture and Design. Proposed AGI Architecture. Building on the insights from the cognitive model, an architecture can be proposed that incorporates the key elements of sensation, perception, action, and self-reflection. This may involve a modular architecture with distinct sensory processing, decision-making, and self-reflective feedback loops, interconnected through an internal representation of the world. Integration of components. The challenge lies in harmonizing the interplay between sensory input, perception, motor output, and self-reflection. This chapter discusses how an integrated system can function in real time, learning and adapting through continuous cycles of input, action, and self-assessment. Challenges and future directions. The implementation of such a model involves significant challenges, including real-time processing, scaling to complex environments, and achieving true self-reflection. Future research may look into enhancing the model's adaptability and exploring its application in varied domains. Conclusion, summary, and key findings. This research demonstrates that a cognitive model based on human sensation, perception, action, and self-reflection offers significant promise for the design of AGI systems. The integration of these components can help create systems capable of adapting and learning in complex, dynamic environments. Implications for AGI research. The findings suggest that AGI systems must incorporate embodied perception, decision-making frameworks, and self-reflection to achieve true autonomy. The development of such systems will require a deep understanding of both cognitive processes and computational mechanisms. Future work. Future research should focus on refining the proposed architecture, developing effective learning algorithms, and testing the model in practical AGI applications, ensuring that ethical considerations and safety are prioritized.